Let's begin our exploration of physical database design. In this video, we will be covering storage structures and access methods, which are vital components in ensuring efficient data management. Here, we will discuss the concept of physical storage hierarchy in database systems. Key characteristics include the use of a storage hierarchy to balance access speed and cost. Data moves between levels, optimized by physical design. This movement significantly impacts query performance. The different storage levels are cache, main memory, flash storage, magnetic disk, and tape storage. Dive into the details of disk storage structure. The main components include platters, which are circular disks coated with magnetic material, tracks, which are concentric circles on the platter surface, sectors, which are arc-shaped segments within tracks, and blocks, which represent the smallest unit of data transfer, typically 4 to 16 kilobytes. Also, cylinders are the same track position across all platters, and read or write heads access data from these platters. Seek time refers to the time it takes to position the head over the correct track, while rotational latency is the time it takes for the sector to rotate under the head. We'll explore various file organization methods commonly used in database management. These include heap files, where records are placed in an arbitrary order; sequential files, where records are sorted by a key field; hash files, where records are placed using a hash function; B-tree files, where records are stored in a balanced tree structure; clustered files, where related records are stored together; and index files, which utilize separate index structures for faster access; and redundant array of independent disks, or RAID, which uses redundant arrays for reliability. Indexing structures are a crucial component in optimizing database performance. Different index types each have distinct characteristics. These include primary index, which is on primary key fields; secondary index, which is on non-key fields; clustered index, where data records are physically ordered; non-clustered index, where logical order is maintained via pointers; dense index, which has an entry for every search key value; sparse index, which has entries for some search key values; multi-level index, which has a hierarchical structure. For example, to create an index named index_customer_name on the customers table, based on the last name and first name, you would use the command create index_customer_name on customers, with the last name and first name in the parenthesis. To create a unique index named index_product_code on the products table, based on the product code, you would use the command create unique index_product_code on products with product code in parenthesis. Let's explore hash-based access methods and how they're used in database systems. Hash-based organization includes static hashing, where there is a fixed number of buckets; dynamic hashing, where it grows with database size; extendable hashing, which uses a directory-based approach; and linear hashing, which splits buckets sequentially. These are perfect for equality searches but not suitable for range queries. Collision handling is critical in hash-based methods. For example, a simple hash function example would be h of key is equal to key mod number of buckets. A collision resolution will be, if bucket h of key is full, place an overflow bucket. B-trees and B-plus tree structures are very important concepts in database indexing. B-tree characteristics include self-balancing tree structure, all leaf nodes at the same level or depth, nodes contain multiple keys and pointers, optimized for block-oriented storage, and efficient for both equality and range queries. In B-plus tree, data is only stored in leaf nodes, and leaf nodes are linked for range scans. The B-tree node structure includes an array of keys, pointers to children, the current number of keys, and it is true when node is leaf. RAID, or redundant array of independent disks systems, is a storage technology that combines multiple physical disk drives into a single logical unit for data redundancy, performance improvement, or both. It includes RAID 0 or striping for performance without redundancy; RAID 1 or mirroring for full redundancy; RAID 5 or striping with distributed parity, RAID 6 or striping with dual parity, and RAID 10 mirroring plus striping. Benefits include improved input-output performance, fault tolerance and data protection, and hot swappable drives for recovery. Let's compare different access methods and summarize the key concepts we've discussed. In this table, we compare access methods based on several criteria: equality search, range query, insert or update performance, and space usage. Sequential files have poor equality search and insert or update performance but excellent space usage. Hash files excel in equality search but perform poorly in range queries. B trees and B+ trees offer good performance in both equality search and range queries. Bitmap indexes perform medium in equality search and range query. Clustered indexes perform good in equality search and range query. In summary, physical design translates logical models to storage. Storage hierarchy impacts database performance. File organizations determine data access patterns. Indexing structures accelerate query processing. RAID systems provide reliability and performance. Key design considerations include query workload characteristics, read-write ratio of application, data size and growth projections, performance requirements, and hardware constraints and capabilities. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.